assignment, or we will have a theory assignment?
You will have also theory assignment that's coming. That's going to probably deploy next Sunday, either 30 October or the 1st
Okay.
November. Before the 1st November, there we are going to deploy the theory assignment. We are already preparing that question for theory assignment. After the graded quiz, you will get that. I already give that announcement, right? In the Slack. I give
Okay, sir.
the three
Thank you.
announcements: one for your lab assignment, one for your graded quiz, and one for your theory assignment. And this will going to the run throughout the semester, alternative way. One week you will get that lab assignment. In the following week you will get that uh, theory assignment as well as quiz, graded quiz.
Sir, our all graded quiz will be MCQ type.
A graded quiz will be MCQ type. Most of the it will be MCQ type. All right, let's start today's topics. Today, basically, we're going to talk about motion in the 1 and the 2D. Uh, Mostly, we are going to talk about that 1D motion today. We'll talk about that 2D and the 3D later on. Basically, the 2D motion is the projectile motion, that you know that one, which is basically that two-dimensional motion under the influence of the gravity that we'll discuss in the later part. All right, so we define the motion actually when a system is moving. So if a car is moving, then we can say that the car is in motion. Can you see my screen?
No, sir.
No, sir.
No, sir.
All right, now can you see it?
Yes, sir.
Yes, sir.
So that's why motion we can categorize the two way. The motion we can categorize, one is known as linear or translatory motion. Second one is rotatory or circular motion. Linear or the translational motion is basically when a system or a car move in a straight line. That known actually the linear or translational motion. And rotatory motion when a particle or the car move in a circular track, that known as actually the rotatory or circular motion. Today we are going to basically talk about that linear or translational motion. To describe the linear and the translational motion, we'll mostly focus on the kinematics of the system. Kinematic of the system will define anything basically which is under my investigation actually. So that's why sometimes I will say the particle or a car, etc. Whatever I'm dealing with, that known as actually the system in physics. So we'll talk about basically the kinematics of the system. Kinematic is basically the mathematical description of the particle or the system. Mathematical description means where would be the particle, what would be the velocity, what would be the acceleration, what would be the average velocity, whatever is the speed, etc. But we are not dealing with that, why it changing its velocity, why it changing in acceleration, and etc. Because that one actually is dealing with the dynamics of the system. Which is known actually dynamism of the system. To describe the dynamic of the system, we need to actually introduce the idea of the force. Since still we didn't introduce that part, We'll talk about that, but after introducing the Newton's law of motion, or the force actually. So then we'll talk about the dynamic of the system, or dynamism of the system. Right now, basically, we'll talk about the kinematics of the system, which is basically the mathematical representation of the particle. To describe the kinematics of the system, we need to use some keyword like, say that position. Position actually the location of a particle at any particular time. Say if you have a car is over here, say that is stationary, and if you want to locate the position of a car, you have to use a reference frame. Say I can say this car at a distance is x, and this x will be as a function of t, because with the time the location or the position of the car will be changed, right? Because the car is not going to stay over here. After a certain time, definitely it will change its position. So that's why this position vector, which is as a function of r, we can retain there will be x t, which is also as a function of t into I head. There's a vector actually over here in the one-dimensional case. That's how we represent the position of a particle or of a car. Now, what about, say, if it is the two-dimensional case? Say in the two-dimensional case, I have a particle like that. If I draw that two-dimensional axis, say this is my x-axis and this is my y-axis. Say I have a car over here. Say this is the point P, and the coordinate of that point P, say that x1 and y1. And I want to locate that position by a vector. Say that that vector is r1 from my this origin or the reference point, right? So this is that r1. Fine. So after a certain time, this position of the particle, say change it from P2, say this is the point Q, which is, say that coordinate is the x2 and the y2, and I also locate that position by another vector, say that which is would be r2. This, say this is actually that r2. Now this r1 vector I can represent by that way. If you closely look at this one would be basically your x1 I hat, and this one would be your y1 j hat. We can use the vector triangle law again over here. So this is to be x1 I hat plus y1 j hat, right? That we can write down. By the same analogy, we can also write down the r2, which would be x2 I hat plus y2 z hat, right? So this is to be basically position of the r1 and the r2 vector. Now, if I want to know what is the displacement between these 2 points, or how much distance is traveled from point P to Q, that would be that one, and that I represent by a vector, say that the del r. My intention is to find out that del r, which is the displacement is traveled by this car from P to Q point. All right, so if we want to find out that displacement, if you closely observe this over here, the vector r1 is connected to vector del r, which they are in a head-to-tail connection. It means that I can write my vector triangle law again over here. It should be r1 plus del r must be equal to the r2, right? We can write that one using the vector triangle law. Now from there I can find out the del r. Del r will be basically r2 minus r1, and I know that r2, which is x2 I hat plus y2 z hat, right, minus x1 I hat plus y1 j hat. Now then I can do some step over here calculation. So I'm going to rearrange this. I will write x2 minus x1 I hat plus y2 minus y1 j hat, right? So this is would be actually the displacement of that particle in between point P and Q. So that's when if you just know the coordinate of those 2 points, then you can find out what would be the displacement of that particle in between 2 points. And since displacement is a vector, it has definitely some magnitude and the direction, right? If you take the magnitude of this vector, you will find out the distance, which is basically the scalar quantity. Remember, displacement is a vector and distance is a scalar quantity. Fine. Now, if I know that displacement, I'll be able to find out that velocity of that particle of or the car. Right. Velocity we define, which is actually the rate of change of position with respect to the time, which is del r over del t. So that unit will be meter per second. If we know that velocity, then we'll be able to find out that acceleration of the system. Right, because we define that acceleration of the system actually rate of change of velocity with respect to the time, and unit to be meter per second square. That is the general way we define, right, velocity and that acceleration. So that's when if you somehow I can find out the position of that particle, I'll be able to find out that displacement. If I know the displacement, I'll be able to find out that velocity. If I know that velocity, then I'll be also able to find out that acceleration of that system. And there is another thing actually we define in our everyday life actually, which is actually the speed. So although we do not make any distinction between the speed and the velocity, but in physics there are some difference between these two quantities, velocity and the speed. Velocity is a vector, it has magnitude and the direction, where speed is a scalar quantity, it has only the magnitude. So speed means basically the how fast a car is moving, whereas the velocity is how fast and in which direction it's moving. That's how we will actually differentiate between these two quantities, velocity and that speed. In general, if the velocity and that acceleration vector of a car in the same direction, say this is that velocity and say this is the acceleration, then the car will basically they speed up. It will generally speed up. If the velocity vector and the acceleration vector are in the two different directions, remember the car will be slow down. That's the general characteristics of this system actually. If these two vectors are in the same direction, the system will be accelerated, or I can say that is speed up. If these two vectors are in the opposite direction, the system will be slowed down. It will be basically the de-accelerated. And one more thing, if that system moves at a constant velocity, say that the v is constant, which means it's not changing with respect to the time, then I can say that the acceleration of that system would be basically 0, because we define the acceleration actually rate of change of velocity. Since the velocity is not changing if it is moved at a constant value, so that's why its acceleration is going to be 0. Now let's talk about one thing which is we define actually is known as the average velocity. Average velocity. Say you are traveling with your brand new car, say starting from this point to that one, and you divided that journey in the two segments. In the first segment, say you have a speed 2 meter per second, and in the second half you have a speed, say that 3 meter per second. Now if I ask you what is the average speed of your journey, probably you are going to say it would be 2 plus 3 divided by 2, right, which is going to be that 2.5 meter per second. That's right, so far so good. But look at this, in your journey in any segment, you didn't move at that speed or at that velocity 2.5 meter per second. In the first segment, you move at a speed 2 meter per second. In the second half, you move at a speed 3 meter per second. But your average speed actually the 2.5, which is different from your actual speed. That's why average velocity actually is not the actual scenario of your journey. It is basically a estimation. It said that if you move at 2 meter per second, after a certain particular amount of time, you will reach that point or your destination. It's giving you an estimation. If you can maintain that 2.5 meter per second in every single minute in your journey, then you can travel or you can reach over there after that a certain amount of time. Yes, known as actually that average velocity. Average velocity is not the actual scenario of your journey. It could be the different. Now, since we are dealing with that kinematics of the system, now how we are going to find out that average velocity? Say a car is traveling, I choose a path. Say this is your xt1, which is actually denoted the position of the car at t1 second. Say this is actually xt2. This is actually xt3. This is actually xt4, and say it's come back again. This is actually xt5, and you can label this is this is t1, this is t2 5, this is t4 second, this is t2 second, and this is actually t3 second. Say you start from there, you go and come back again over here, your origin, and I choose, say this is my positive x direction into that way. Now if I want to find out that average velocity in between any time, say I'm choosing say t1 and the t2 second, I will write down this one x t2, which is the displacement at time t2, minus x t1 divided by t2 minus t1 into I head, right? Why? Because generally we define that velocity actually rate of change of position with respect to time. I'm taking time in between t1 and the t2, so that's why at t2 time in position actually xt2, and at t1 time in position was xt1. I take the difference of that displacement. Then I will find out this will be your average velocity. And in a short form, we write this would be basically the del x over del t I hat for the one-dimensional case. If it is two-dimensional case, then we'll write that average velocity, which would be del x over del t I hat plus del y over del t z hat. So this would be basically that general formula to find out the average velocity of a particle. If it is three-dimensional, you have to add one more term, that would be del z over del t into k head. So that's how actually you can find out that average velocity. Now this average velocity, you can say that it would be, say, greater than 0, it could be equal to the 0, and it could be less than 0. Greater than 0 means which is actually the positive quantity. Less than 0 means it will be negative quantity, and 0 is 0, right? Now for this case, the journey I draw over here for this one, I can say that average velocity in between time t1 and t2 would be greater than 0, Why? It greater than 0 means positive quantity. It basically moving in the direction of my positive x direction, right? I'm moving from xt1 to xt2. So that's when I'm heading towards that positive x direction. So that's why I'll find out that average velocity will be positive in between time t1 and the t2. Then the average velocity in between, I can say that time t2, t4 would be less than 0. In that case, I'm basically moving from xt2 to xt4. If you take the difference, xt4 minus txt2, that would be negative quantity because xt2 is larger distance with respect to the xt4. And this will be give you basically the negative quantity, and you will come to actually basically towards the opposite direction. So that's why it would be negative. And the average velocity in between time t1 and the t5 is going to be the 0 for this case, because my displacement is 0. So that's why the average velocity for this case, it would be 0. It will be always 0 if your initial and the final point are the same. The average velocity will be always 0 because in that case, actually your displacement is 0. Now, what about if I say the average speed? Will the average speed in between time t1 and the t5 will be 0? What about the average speed? If I ask you, is the average speed in between time t1 and the t5 will be 0? It's not going to be 0. Remember, average speed is a scalar quantity that we define actually the total distance, which is actually the scalar quantity distance divided by total time. So that's mean whatever the distance, if you say from here to here, say if I say from that point to that point, say that 5 meter, this 5 meter you go over there at xt3 and you come back to that point again 5 meter. In that case, 5 plus 5 divided by time you take, that would be your average speed. Average speed is not going to be 0 for this case. Average speed actually the total displacement divided by total time. So that's why the average speed in between time t1 and the t5 is not going to 0. Remember this point, because we define the average speed actually total distance divided by total time, which is basically the scalar quantity. Say sometime it could be possible, say if you start from that point, you go over there and you stay over here. So sometime you spend over there, you take some break and you again come back over here. So in that case, you have to also count down the time you spend over there. That would be your total time of your this journey. That's how actually you can find out the average speed. All right, let's talk about that instantaneous velocity. Instantaneous velocity. Instantaneous velocity actually the velocity of a system or of a car at a particular time. So suppose when you are driving your car, there is a speedometer in your car, and in that speedometer there is an indicator that indicate the speed of that car in a time or in a particular amount of time, and that indicator always in a oscillated mode. Actually it oscillate that one. So once you look at that speedometer, whatever the position of that indicator, that is the speed is indicating, that is the speed in that particular moment when you look at that speedometer. That is actually that instantaneous speed of that car. Now, how we are going to find out this instantaneous speed of this car? Say you are moving with your brand new car. You want to say for simplicity, I replace that car by a dot over here. There's a reason why I'm doing that. So this is actually your car. Right now, I want to know the position of that car just right after that point. So this is the black dot, your car, and I want to know the position of that car at the position which is I marked by the red one, which is just right after that black dot. Right. So this is a very small distance. Say if you locate this x, actually that t, the position of that particle at time t, and this we can write x t plus del t. Del t actually is a time which is very small, is a fraction of second, which is close to the zero, but not exactly the zero. We're thinking in that way. So it will, that's mean del t actually the time it will take to travel from black dot to red dot, which is just right after that black dot. It's a very small distance, so that's why it will take a small amount of time. All right. Now, if I want to find out that velocity, in this case, I can write this velocity. I will define, say that displacement between these two times, t plus del t, which is that final point, minus xt, which is the initial point, divided by difference of the time, t plus del t minus t. And we define that there is a case, actually the limit del t tends to 0. So that's when t not exactly the 0, but it's close to the 0. Right? We can define in that way. Then this v we can write down in another format actually. So you can write, say, x t plus del t minus xt divided by del t, because this t will be cancelled out, right? Now, can you say this is a definition of some function in the mathematics actually you define? What is that? Are you familiar with this term? Can you recall this one? You already know this thing at your higher secondary level. Or secondary level, probably they introduce this idea. What is this? Can anyone say me that one? What is this?
Which one, sir? It's a
This
limit.
one, I make a box.
It's a limit, a process of differentiation.
It's a differentiation. It's a definition of the differentiation of that function v, right? With that define actually dx over dt. It's a very important thing actually. Say I draw, for simplicity, I just drop that vector sign, or only for the simplicity. So I just drop down that vector sign over here. So this would be the definition of that differentiation. It's a mathematical, because we are dealing with the mathematical representation. We'll talk about this mathematics. Without mathematics, I cannot move a single step forward. Mathematics is a very useful tool for me, or physicist. So that's why we define in an instantaneous velocity using that one actually. So that's when if you know the position of a function, if you take the first time derivative, that will going to give you the velocity, and in that velocity, if you plug in that particular amount of time, that is going to give you that instantaneous velocity in that time. That's how actually we define that instantaneous velocity. And if it is one-dimensional, you can write in that way. If you want to express in the two-dimensional case, I'll write down dx over dt I hat plus dy over dt z hat. If it is three-dimensional, there will be one more term. That would be dz over dt into k hat. That would be that, basically that instantaneous velocity of this case. Now say, if you think about in that case, if you have, say, this is actually the displacement versus time curve. So this is the displacement versus time curve. So this is actually that curve. If you take the dx over dt, can you say that what it will give you from this curve in a sense of mathematics? If I take this curve actually x versus t, if I take the dx over dt, what it will give me from this curve? in a sense of mathematics, not the physics. Physics, we define that actually the velocity we write down over here, right? But what it will give me from x versus t curve. No one know that one? Am I disconnected from you guys? Hello?
No, sir.
No, sir.
Then respond me. If you do not respond, then I will assume that I am totally disconnected from you. Can anyone say me that one, if I take that dx over dt from x versus t curve, what it will give us? Come on guys, you know that one.
Sir, dx by dt.
Yeah. From
Sir,
this
it's
x.
velocity. Velocity.
So that's the physics point of view, that we define the velocity. But what about that mathematics point of view?
Slope.
It's a slope. It's a slope. Physics come later, math come first, right? Physics is actually the application of the math. We define that slope actually in physics give me that velocity, dx over dt. It's very important. You have to understand this graphical representation also. So that will give you basically the slope of this curve x versus t. All right, say, and this instantaneous velocity is also could be, say that greater than 0, it could be equal to the 0, and it could be also the less than 0. I'm coming to that point when it will be that. Say for example, if we say I'm going to draw a curve over here. Displacement versus time graph. So this is my time. I should make it. So this is my time curve, time axis, you can say that, and this is my displacement axis. Say I write, say this is actually t1 time, this is the t2, this is the t3, this is the t4, this is say the t5. Now say the car which I describe the journey actually. This is the trajectory of that. So this is the curve. That's the way. I can label, say this is my swan time. This is T1. This is T3. This is T4. And sorry, so this is actually T5 will go over here because I make that one come to actually it's this would be T5 because it's come to its initial point, so that's why it should be that one. And say I can write, so this is xt1, that distance would be xt3, that distance would be, sorry, it would be xt2, it would be xt3, this one would be xt4, and this one will be xt5, right? We describe in that way. Now, since we say that the dx over dt basically the slope of this curve x versus t, right? Then I can say the slope at that point over here is going to be the positive. If you take the slope over there, this is also going to be the positive. Or in between time, if you take the slope t1 from t2, that's going to be the positive, right? Or in between time t2 and the t3, that would be also the positive. But in between time t2 and the t3 and the t4, that's going to be the negative. Or t4 to t2 at that point is going to be the negative. Slope would be negative over here. So that's why I can say that instantaneous velocity for this case, say t1 or t2, it would be greater than 0, and that the instantaneous velocity in between t4 and the t5 is going to be negative over here, right? Am I right?
Yes, sir.
Now what is the slope at that point t3 over here? What is the slope at the top point over here of this curve?
Sure, maybe 0.
Maybe it should be 0. Maybe why you are saying that? It
Um,
should be 0.
Yes, sir.
You should know this one. Remember, this is the prerequisite of this course. It's a calculus-based course. You have to
Yes.
understand this thing. Otherwise, you cannot penetrate, or you cannot actually explain this thing, why it is so. Remember, math is a very beautiful tool to explain your science. It's a very powerful tool. We are using that tools. Definitely that slope at the point t3 is going to be the 0 at point this one, that point, and that point is basically that slope is 0. That's why the instantaneous velocity at this point is also going to be the 0. At this point, and this point is basically the instantaneous velocity is going to be the 0. Now, what is this physical significance of this one? This one actually you are moving towards in the positive direction. In this region, you are moving to the basically the negative direction. So that's when your slope is negative, you are moving in your opposite direction. The direction you take the positive, you are moving in that opposite direction. If your instantaneous velocity is negative, if your instantaneous velocity is 0, then you are changing your direction. That is actually the turning point of that curve. This is the turning point. So that's mean, say when you make a turn in the road, so this is the road, you are going to make a turn into that way. So at this turning point over here, the speed of your car will be basically 0. Although you make a successful turn due to inertia of that car, but the velocity at this turning point must be going to be the 0. That we say that the car will be momentarily stopped in physics. When the instantaneous velocity is 0 means we say the car will be momentarily stopped at that point. Although in real life we can make a successful turn due to the inertia of the car. If you have somehow can stop that inertia, car will be stopped at that point. That's the meaning of the instantaneous velocity 0 means. The instantaneous velocity is 0, then we will say that the car will be momentarily stopped at that location. That is the physical significance of this instantaneous velocity 0 means. All right, let's talk about that average acceleration in that case. Average acceleration that we can define by the same analogy. We'll write down, say that average acceleration in between time t1 and t2, that journey I described with your brand new car. So I'll write down the change of velocity, which is vt2 minus vt1. It's a vector divided by t2 minus t1, that we can write. So it should be del v divided by del t, right? So and it will be basically meter per second square. If it is two-dimensional, then we'll write down this equation del vx divided by del t I hat plus del vy divided by del t z hat. So that would be basically that average acceleration of a particle in the two-dimensional case. where del Vx actually the difference of the velocity along to the x direction, and this is del Vy actually this difference of the velocity along to the y direction. That's how actually we can find out that average acceleration of a particle of the curve. And this average acceleration would be also greater than 0, less than 0, and it could be also equal to the 0. You can find out in that way from the curve. And what about the instantaneous acceleration? Instantaneous acceleration we can also define. So the function we're going to define, it will be basically that limit del t tends to 0. It will be change of velocity, right? We'll write down vt plus del t, which is the velocity at the final point, into vt divided by t plus del t minus t, right? Difference of the time. So it will be limit del t tends to 0. I'll find vt plus del t minus vt divided by only that del t, which is would be basically that definition of the differentiation of that function. I can write this would be basically dv over dt, right? It's with the vector, I'm sorry, or I should use that sign over there. And I know this velocity function for the one-dimensional case, or in instantaneous velocity, we write down dx over dt into I hat. Then we can write this acceleration would be d square over dt square into I hat. That would be the instantaneous acceleration. That's when if you know the position, you have to take the second time derivative to find out the instantaneous acceleration. After taking the second time derivative, if you plug in your desired time, you can find out the instantaneous acceleration in that particular time. If you consider for the two-dimensional case, that would be dx square over dt square I hat plus dy square over dt square z hat. So that would be basically your instantaneous acceleration formula. Using that formula, you can find out that instantaneous acceleration. Now from this one, actually, we can also basically find out that whether this particle will be moved at a constant velocity or constant acceleration, or neither not, if you closely observe that curve of that one, right? So roughly you can say that in between that two region, actually car will move at a basically that almost constant velocity, right? Because it's not changing, it's not abruptly changing actually, but over here it's changing is this velocity. You can say that the velocity is changing. You can say in that case it will move at a constant acceleration. You find out that one. That depend actually some equation. We are going to find out that equation whether the particle moves at a constant velocity or constant acceleration. Mathematically, we are going to represent that one. We'll derive that equation. Not the derive, I'll show that one actually. Say a car is moving according to this equation. Say I should write this is a function of time. Say 8 minus 6t plus t square into meter. Car is traveling according to this equation, and it's a time dependent function, right? If you plug in the different time, the value of x will be the different. For example, if you plug in the t equal to 0 second, you will find out the x will be the 8. If you plug in t equal to 1 second, that's going to be the 2. No, it's going to be the 9. It's going to be the 3 probably. One is, yeah, it's going to be the 3. So that's mean the position is changing. Now, if I want to find out the velocity, that I'll write dx over dt. That will give me, what will be the derivative of this function?
Minus 6 plus 2t.
Minus 6 plus 2t, right? It's a meter per second. Now velocity is also, look at this, I just dropped that vector sign since I'm only do the calculation over here. So, but you have to express that one. If velocity is a vector, if you talk about the velocity, you have to give the direction also. Now, it's a one-dimensional case I'm talking about. We can also deal with the two-dimensional case. We'll do that in the later part. Fine. So now look at this. This velocity is also is a function of time. Is will be different at different time. For example, if you put t equal to 0 second, your velocity will be -6. If you put t equal to 1 second, your velocity will be -4. That's when it's changing, right? I can say then the particle, if that particle is not moving at a constant velocity, right? Because velocity is changing. That's fine. Now, what about that acceleration? To find out the acceleration, I can take the first derivative of the velocity function or the second derivative of that position function. And if I do that, I'll find out it will be basically plus 2 meter per second square, right? Which is basically a independent of the time function. It's not depending on the time. So that's when I can say the particle will move in at a constant acceleration, because acceleration is not changing with time. That's how we define it the constant. Is anything is not changing with time, that we define as a constant. That is actually, we can say from here, we can say that the particle will be moves at a constant acceleration if the particle moves according to this equation. So that's when if you just look at this equation, because it's a second order equation, if you take the second time derivative, that function will be independent of that t. So that's why the second time derivative quantity will be basically independent of that time t. So that's why we define the second time derivative of position function is acceleration. That's why we can say that the particle will move at a constant acceleration over here. If say the function is the t cube, say if the function is over here instead of t square, if I say the t cube, then I'll find out the a as a function of t, right? In that case, the acceleration will be not constant of that particle or the car. The acceleration will be changed. If the acceleration is a function of time, then it will be different at different times. So that's when if you closely observe this equation, just look at this equation, you can say that whether the particle moving at a constant velocity or constant acceleration or neither not. All right, let's take some data from here. What I'm going to do, I'm going to say that find out at time t equal to 0 second, I want to find out that velocity. So I'll write x naught actually the time t equal to 0 second, it would be 8 meter, v naught, that would be -6 meter per second, and a, which is independent of the time, that's going to be the 2 meter per second square, right? If I just plug in the t equal to 0 in these three equations. All right, now I want to know when x equal to the 0. So that's when I want to find out when the position of this particle will be the 0. So that's when it was at the origin, where I choose that origin. Or fine, to find out that one, I'll plug in that value of x into that equation, displacement equation, which is 8 minus 6t plus t square. Now it's a quadratic equation. You know how to solve this quadratic equation. If you solve, you'll find out the two value of this t. It has the two root. One will be 2 second plus 2 second, and fortunately the second one is also that plus, that would be plus 4 second. You can check that. You will find out that both two are root are positive over here. So that's why I have to take the both of them. If one is negative, then I can drop the negative time, right? Because we do not consider that time is negative. Time cannot move in the backward direction. We consider in that way, right? Since it's the positive, I have to take the both two time over here. All right. Now I want to know when v equal to the 0. That I can find out. I'll just plug in that v equal to 0 into that equation, -6 plus 2t 0 equal to minus 6 plus 2t, then I'll find out t would be basically that 3 second, right? To plug in t equal to 3 second, your velocity will be the 0. And find out when the velocity actually the 0, what is the location of that particle? When v equal to 0, what is x? So that's mean when v equal to 0, where is the particle or what is the location? I know v equal to 0 at t equal to 3 second. I'll plug in into that into my equation, which is 8 minus 6t plus t square. If you plug in at t equal to 3 second, this x3 would be basically the minus 1 meter. I'll find out the position of that particle would be minus 1 meter. All right, I'm going to basically draw the curve of this journey, whatever the equation is given over here. So this is my time axis, and say this is my displacement axis. All right, so this is actually t. This is my displacement, and I choose this is my origin. Say for simplicity, I write down, say this is 2, 4, 6, and 8, and 10. This is the 10. And say this is 1, 2, 3, 4, 5, 6, 7. This is the time scale I level. So 1, 2, 3, 4, 5, 6, and 7, so on. So this is will be the 2, 4, 6, and 8. And this is my origin. And I can say this is say that, or I can say this is the minus 1 to make the curve. Although this is in the all right. So single division actually basically 1. I choose in there. This is the minus 1. Now, when t equal to the 0, my location was over here, right? Look at this. When t is equal to 0, I find out that data x equal to plus 8, v equal to minus 6, and a equal to plus 2 meter per second square. I'll plug in that data over here. So acceleration is the plus 2. I can say that would be toward the upward direction, which is plus 2 meter per second square. Velocity is the minus 6. I can say this is would be downward meter per second, right? So that would be, and this would be your location. You are over here at that 8. Now at t equal to 2 second and the t equal to 4 second, you should be at the origin. Your displacement actually is basically the 0, right? I find out at t equal to 2 second and t equal to 4 second, your displacement is the 0. And t equal to 3 second, you are at that minus 1 displacement. So that's when you would be over here. Now, since starting that point, I find out that these two vector velocity and the acceleration in the opposite direction. So I can say the car will be slow down, right? So that's when it will be deaccelerated. Then I can draw that one, that curve actually. It will come to that point at t equal to 2 second. It must be at that over here at the origin. T equal to 3 second, it would be at x equal to minus 1. And since the velocity is 0, at t equal to 3 second, it will make a turn. And it will again t equal to 4 second, it will be at that origin. And that's how it will be moving that way. That's mean this is would be basically that trajectory of that particle. In that way, it will move, right? So that's when using that formula, actually, we can also depict that journey. That's why if you want to represent the general displacement formula will express by that form. It would be x equal to c1 plus c2t plus c3 t square, where c1, c2, and c3 is basically the constant. I'm going to find out that constant over here, because look at this, the position function for that curve I draw, it was 8 minus 6t plus t square. right? Is it similar to that one? I'm going to find out the general case, actually C1 and the C2. To find out, say, first I'm going to find out the velocity. That would be dx over dt, which I can write since C1, C2, and C3 are the constant. If I take the derivative of the C1, that should be 0. I'll find out C2 plus 2 C3 into t, right? What about the A? A would be dv over dt. That's going to be the C2 is again 0. It would be basically that 2 C3, right? Now I'm going to find out this quantity at t equal to 0 second. I'll write, so this one, if I plug in t equal to 0 second, what I'll find out, this one will be cancelled out because it's 0. I'll find out x naught would be C1, right? V naught would be, if I plug in the t equal to 0, V naught would be C2, and A, which is independent of the time, that would be actually that 2C3, or we can write C3 would be basically that half of A, right? Now we can write down the general formula of the displacement. I'm plugging, this is x naught, this is V naught into t plus half of A into t square. I just plug in the value of C1, C2, and the C3 into that equation, which is actually that most general equation of a displacement of a particle. And this is this equation is basically most important equation. Although this equation is not new for you, probably you use this equation in another format actually, which is UH equal to UT plus half of AT square, right? This equation is familiar to you, but this is very special case. When saying that is special case, when you use this formula, you already assume that you starting from your origin, but this couldn't be in real life. Like this one, your origin is over here, but you start from that point, you are not at that origin. It could be, so that's why because this formula is a very useful. And remember, I said you have to at least carry some information when you're going to through this course. Some information you have to carry in your head. Among them, I said that one is the vector triangle law, right? Still we are using that one. And second one is actually this equation, general displacement of a equation. Using that equation, we can define whether the particle will move, 1 minute, whether the particle will move either constant velocity, constant acceleration, or neither nor, using this equation. And using that one, whatever the other formula you memorize, actually v equal to u plus at, or v square equal to u square plus 2ax, all the formula could be derived from that one. You can check. So if I want to find out the velocity from this equation, dx over dt, x naught will be 0 because it's a constant. You will find out v naught, t will be vanished, and it will be half of a into 2t. This will be cancelled out. We will find out v will be basically v naught into at, right? We'll find out v naught plus at, which is exactly v equal to u plus at. The other formula could be also the direct. So that's why this would be most general equation of this displacement. I'm going to use this equation any type of motion, even though the projectile motion, whether it's a 1D, 2D, projectile is actually the two-dimensional motion under the influence of the gravity. So in the case of the two-dimensional motion, I will represent this equation. X would be x naught, v naught x into t plus half of ax t square. V naught x actually the initial velocity in the x direction, and for y direction we will write down the y naught v naught yt plus half of ayt square. That would be the case for that projectile motion. I will use simply this equation, one equation. It's a second one we write in the same way, right? So only that equation you can explain any type of motion, whether it's a 1D, 2D, whether it's a move a constant velocity, constant acceleration, neither nor. All the motion we will define by this format, actually, this equation. All right, go on for who wants to ask me a question. Yes, is there any question over here? Hello?
No, sir, it's all right.
No, sir.
But remember, when you're going to use this equation, the acceleration due to gravity, which is vertical direction, Ay, if you write down the vector form, which is sometimes you can write the Ag, acceleration due to gravity, it will be always minus 9.8 J hat, meter per second square. You have to always use that acceleration due to gravity would be minus 9.8 for this case, if you want to use this equation. So it doesn't care about whether you move to the upward direction or downward direction. Acceleration will be always negative. Sometimes some students tell me that, I don't know why they do that. Some students say that when it's moving to the upward direction, a particle, acceleration will be positive. When it's moved to the downward direction, it will be negative. Someone say when it's moved to the upward direction, it will be negative. When it's moved to the downward direction, it will be positive. I don't know whether they flip that direction. Why they do that, I don't know actually. I don't have any idea. Because once you define your Cartesian coordinate in that way, this is your positive x direction and this is your positive y direction. Any vector goes toward that direction, I'll say the positive. Any vector goes toward that direction, I'll say it would be negative, right? That's our idea. It doesn't care about whether you move to the upward direction or downward direction. Acceleration due to the gravity is always downward, net to the Earth's surface, right? Because that acceleration arises due to the attraction of that Earth, which is actually attracting everything towards it itself, which is downward. And that's why, since the force is downward, which is applied by that Earth, then the acceleration would be also the downward due to that gravity. So that's why it will be always downward. Acceleration would be minus 9.8 meter per second. Whether it moves to the upward or downward direction, it's not going to be that change its direction. I understand is little bit part. So they have flipped their direction. If you say when it's moved to the upward direction, they consider that it's a positive direction. When it's moved to the downward direction, they flip that this downward y would be then actually that negative direction. But we don't have to basically, because acceleration is always downward due to the gravity. So that's why we'll always use this acceleration due to gravity will be minus 9.8. You don't have to flip your direction of your axis. And remember this point. This is a very important point. I will always use that g, acceleration due to gravity, will be minus 9.8 if I want to use this equation. All right, let's discuss one more issue actually. Sometime you have to basically find out, say you have to do the integration, reverse, say if you have the velocity dx over dt, you know that velocity, and if you want to find out that position, what was the position at that particular amount of time, you have to do that integration. We can write from this will be dx into v into dt, right? If we integrate from there, we will find out actually that position from there, because is the velocity would be basically that function of t. Like you will find out, say there will be also some limits, say that x into x1 to x2, and it would be say that time t1 to t2. In the previous case, we find that velocity actually say that minus 6 plus 2 is t. If I integrate this one, I'll find out, say for example, it would be x t2 minus x1. If I plug in, if you take the integration of the dx, you will find out the x. I'm plugging that limit x2 minus x1, and this one you will find. I make a jump over here. I'm sorry. Should write down one more line so that you can understand. Say I'll write it would be x1 to x2 is the dx. I can write t1 t2 v would be minus 6 plus 2t into dt, and you can find out that one it would be x1 to x2, and this would be minus 6 into dt if you integrate t1 t2, right, plus 2 t squared divided by t t1 t2, right? So that's when I can find out that what the displacement at that particular amount of time. So you can do in that way integration. You have to do in that way. Or if you want to find out, say that if you know that acceleration, if you want to find out the position, you have to take that second time derivative. You cannot take that second time derivative at the time. You have to, in that case, you have to do that step by step. First, you have to find out that velocity, which is actually dv over dt. If you take that integration, dv into a into dt, if you take that integration over here, you will find out that velocity in some function. And to find out the displacement, you have to take that derivative of that velocity again. Then you can find out, you can follow that procedure to find out the position displacement by that integration. In the both way, you will be able to find out that parameter of this one. All right. One more thing. Can I take? Still, we have the time, right? Fine. So I'm going to use an example from this case. Say, you're standing at the ground floor over here, and one of your friend is standing at the window of a building, and the distance between you and your friend is, say that, 4 meter. What you did, you threw a ball towards your friend, and after 1.5 seconds later, it was caught by your friend. Now they asked us what was the initial velocity of that ball. So that's mean, at what velocity did you throw that ball towards your friend, and what was the velocity of the ball just before it was caught by your friend? That is the question they asked you. So that's been the initial and the final velocity, both velocity they asked to find out. Now, if you want to use that formula, which you say v equal to u plus at, which is actually used for the particle moves at a constant acceleration formula, right? The formula we talk about is still that one, actually, that the particle moves at a constant acceleration because it's the function of the t square, quadratic equation of t. So it's, if you take the second time derivative, t will be vanished. Then you can say that the second time derivative actually we define the acceleration, and the acceleration will be a constant. So that's why these are the equation of a constant motion equation. Whatever you write, h equal to u plus at, half of at, and v equal to u plus at, or v square plus u square plus 2ax. These are the equation of constant acceleration motion. Fine. Now this formula is not going to work because both the case, actually v and the u are actually that unknown over here. What I'm going to do, I can use that equation, since this is my positive y direction and this is my, I'll say this is my positive x direction. All right, then I'll write y equal to y naught v naught yt plus half of a yt square, right? So if I choose this is my origin, then I can say this y naught would be 0, and the y actually the displacement between these two guys, and y naught actually the 0, v naught y, which is the initial velocity. At that velocity you throw the ball towards your friend, that we have to find out, into t is 1.5 plus half ay would be minus 9.8 into 1.5 square. Then you can solve this only. If you solve, you will find out the v naught y, that is the velocity, initial velocity along to the y direction would be 10.01 meter per second. So this is actually that the velocity, the ball, it was thrown. At that velocity, it was thrown. Now you can use that this formula, final velocity, to find out v y equal to v naught y plus ayt, which actually your known formula, v equal to u plus at, but I write them that way. So vy is the final velocity I have to find out. V naught y actually 10.01 minus 9.8, because g is 9.8, into t is 1.5, right? Then we can find out that final velocity vy will be minus 4.69 meter per second. It will be the minus. Now, what is the physical significance of this minus sign? What it is actually they're telling us? It's telling us that when you throw the ball, it is basically moving to the upward direction. It goes to the upward, it is to the maximum point, then it falls to the downward. That's why the velocity is the downward direction. It will be negative. It means that when it's moving to the upward direction, it was not caught by your friend. It moves to the top point, become velocity 0, then it moves to the downward. When it's falling to the downward, at that time, it was caught by your friend. That is the physical significance of this minus sign. That's why this equation is very interesting. And this is one of my favorite equations. Somehow you have to get this equation. And this is the most beautiful equation. Using that one, you can actually explain any type of motion. You can also actually tell what is explain that thing actually that way. That's why I'm requesting you guys have to somehow cope up with this equation, because I'm going to basically describe that projectile motion using this formula. Only using this formula actually will explain that projectile motion. You don't have to memorize any equation, maximum height or time to reach the maximum height, flight of time, range, blah blah blah. Forget about this thing. Using that formula, you can explain any type of motion. Whether it's a 1D, 2D, whether it's a move a constant velocity, constant acceleration or line and not. Everything could be explained in that way. All right, that's all for today. Do you have any question over here?
No, sir.
No, sir.
Then you can leave.
Okay, sir. Allah Hafiz. Assalamu alaikum.
Assalam.
Sir, I have a question.
Sure.
Sir, the question is about